The first statement I want to make, and again, nothing new yet, but velocity is the slope of the position graph. Nothing new there, right? And we could go one step further. Acceleration is the slope of the velocity graph. All good so far? Change it over here is remove the word graph and write the word function. The velocity function is the slope of the position function. That changes this from algebra to calculus. Same here. Function. The acceleration function is the slope of the velocity function. So today I want to show you how to use calculus to do that. And I'm going to stick with what we know. I'm going to stick with simple examples. But you are going to learn the polynomial process. We're going to learn this for polynomials. Why? I hope you understand why. The right board should be telling you why we're doing this for the polynomials. Don't you notice that all these are polynomials? Now, as the year progresses, we will have other functions, and therefore I'm going to expect that you will learn more than just the polynomial process. You're going to have to learn this for the trig functions. You're going to have to learn this for the exponential functions and the logarithm functions and all of those. But today we're going to start with just the polynomial process, okay? The polynomial process is all we're going to need to know. So to do that, I want to do a couple things to remind you, but I want to start with a polynomial. This is a polynomial, right? Now, it's because of last class period, I gotta say some things. This is a single nomial, a monomial, so to speak, one term of a polynomial. So this polynomial has 3 terms in it, correct? So as we say, polynomial probably just means multiple terms. So anything that is added or subtracted, each one of those is a term, as long as there's nothing specific in the function. We would say this is a second order polynomial because it's t squared, right? You learn terms like that, so those terms can be applied here. I don't have to worry too much about that. I'm not going to stand on circumstance. I am going to say that the phrasing from earlier, velocity is the slope of the position function. You're used to, or you know, slope as delta y over delta x. Don't write that down. We're not using y and x, and you know it. So if I want the slope of the position function, well, it's position on the vertical axis and time on the horizontal axis. Back to white. There we go. I don't know what happened there. Now, this is only useful if you can take 2 points and find rise over run. We can't do that for something that curves. So we're going to change how we write this. We're going to change the deltas, the Greek letter, lowercase d, and put them as lowercase d's, just in regular Roman lettering. Now, if you go on in math, there's lots of symbology surrounding slope and surrounding the derivative. There's different d's that are used to mean different things because we have partial differentials, and there's lots of stuff out there. The standard lowercase d suggests that you are applying a derivative to a function. In fact, the easiest way or best way for me to write this is to write it like this, that we are doing something to the function. Now, that's not exactly true. I'm not lying to you. I'm just leaving out some specifics, okay? There's some things here that I need to just kind of gloss over for now until you become accustomed to this and buy in a little bit, and then I'll go back and I will kind of fill in some of the gaps. But what I'm not going to do is I'm not going to tell you why this works, okay? If you want why it works, you know the answer to that question. Go talk to Mr. Brashear or Ms. Smith. They'll teach you why this works. They'll give you all sorts of theory as to why this works. I will just provide you with evidence that it does work. Is that okay? All right. So first, there are two things about the derivative that you need to know before we even get started. The first is that you can apply the derivative to both sides of an equation. It's like squaring both sides of an equation or multiplying the same thing on both sides of an equation. You can take the derivative of both sides of an equation. So if I'm looking up there as to how this is going to look, I would say I'm taking the derivative of the function of x, which is to take the derivative of 1/2 times negative 0.5 t squared plus 3t plus x naught. Okay? I can take the derivative of both sides of an equation. Now, before I go on, this symbology, this whole thing means taking the derivative with respect to t of the function x as a function of t. That's how you would say this. You are taking the derivative with respect to t of the function x. Okay, that's how we would say it. All okay? That's how I want you to approach this. Now, there's something important about the with respect to t. If I look back at the equation, I have t right down there. Any t in the function is important. And any other symbol that is related to t is important. But anything that is unrelated to t, meaning anything that does not change with respect to t, anything that is a constant, is unimportant. We only care about the things that are with respect to t. So when we say with respect to t becomes important. It's the variable. Anything else is a constant. Because you're going to have to take derivatives of things that don't always have numbers in them, that are a whole bunch of symbols. Whatever is here, that's the important functional variable. You're taking the derivative with respect to that functional variable. I'm saying it this way because the polynomial process looks something like this. I'm taking the derivative of a polynomial, x to the n power. The derivative is n times x to the n minus 1. This is the polynomial process. Okay, that is the process. We'll have a different process for different functions. That is the process here. Okay? So you're just bringing the exponent down in front and subtracting 1 from the exponent. You do it one time. All right, let's see what this looks like in practice. So, first things I want you to consider is that the derivative obeys the distributive property. So I can distribute the derivative to each term. So I have distributed the derivative. Next, anything that's not t is a constant. And anything that doesn't change with t is a constant. They can be ignored and brought out front. For example, 1/2 and 0.5. Do they change when t changes? They are constants. They can be brought out front. Is 3 related to t? Does it change when t changes? No, it's a constant. We brought out front. Now, do you see a t here? No. So, if you don't see a t, there is an implied t. T to the 0 power. Because what is t to the 0 power? 1. So, bring x naught out. It's a constant. d dt of t to the 0 power. Now, look, I'm writing out a ton of extra steps. You understand that you probably won't have to do this if you kind of catch on to what's happening. But for now, you may have to write it all out. This is still dt of x. Now, I'm going to apply the polynomial process. I still have my 1/2 and my negative 0.5. But the polynomial process says to take the exponent, bring it down front, and then subtract 1 from the exponent. Polynomial process, right? Bring the exponent down front, and then take 1 away from the exponent. Let's go to the next one. That t is just t to the what power? T to the 1 power, it's implied. So I bring the 1 down front, and then t to the 1 minus 1 power. Okay? Plus x naught. I bring the 0 down. Does it matter what I do to that exponent now? No, because the 0 will wipe out anything that's there. Now, before we go any further, I didn't have to do all that rigmarole to show this is 0. Does x change as t changes? X is just where the object started. Does that change when time changes? No. So we're trying to figure out how the function changes with respect to time. Would that constant be changing with respect to time? No, it was going to disappear either way because it doesn't change with respect to time. I'm just pointing out, though, that this is why it goes to 0. It follows the procedure. Now, let's just clean this up a little bit. I have a 2 times a 1/2. That goes away, right? But I do still have negative 0.5. T to the 2 minus 1 is just t to the 1 power. Correct? All right. 3 times 1 is just 3. T to the 1 minus 1 is t to the 0 power. Do I have to write it, or can we just assume it's an implied 1 and it disappears? And the derivative gives me the slope of the position function, which we know to be what? Start all the way at the beginning. What do we know about the derivative or the slope of the position function? It's velocity. So this equals v. Now, this isn't a surprise. Please look on the other board, right? No surprises, right? It had to work out that way. It had to be able to be shown that when I take the derivative of the position function, I get the velocity function. These are all based on the same math. Calculus isn't not algebra, it's just more algebra. So it has to produce the same answer. Now, I know that that's not why it works, but it's in support of that it works. Okay, so I hope so. Before we go on any further, I find it always best to make you practice this again, to make sure you kind of got it down, and to maybe throw you a loop here or there. So we're going to practice this real quick. Let's just imagine I have this function. This is my functional position as a function of time. Can you find me the velocity function? I'm not going to write out all the same things I did before. The only thing that's important are the t's. Everything else is going to be treated as a constant. So I'll go to my first term, because I'm taking the derivative with respect to t of the whole thing. But I remember it can be distributed. But that's going to give me the velocity function. So here we go. Bring the 4 down. Negative 2 times 4 is negative 8. T to the 4 minus 1 is 3. That's my first term. Move to the next term. Bring the 3 down. 3 times 6, 18. T to the 3 minus 1. 3 minus 1 is 2. Excellent. Go on to the next term. Just because the exponent is negative doesn't mean this doesn't work. I said it works for all polynomials. So it works here just fine. Bring down the negative 2. Negative 2 times negative 3 is positive 6. T to the negative 3 power. I still subtract 1. The process doesn't change regardless of the exponent's positivity or negativity. 4 is a constant. Its derivative is 0. This is the velocity function. All good?
Yeah.
What's the acceleration function? Acceleration is the slope of velocity. So you just do this again. If v equals dx dt, because velocity is the slope of position, acceleration is the slope of velocity. It's just going to be the next thing. I'm going to take the derivative again. How we doing? Somebody want to tell me what the first term is? First term.
Negative 24 t squared.
Negative 24 t squared. Somebody raise your hand, give me the second term. Go ahead.
Plus 36t.
Plus 36t. Somebody else give me the last term. Go ahead.
Minus 18t to the negative 4.
Minus 18t to the negative 4. Excellent. Excellent. Not a problem yet? Okay. So let me just throw a few things at you, okay? How about a question like, where is the object when the velocity is 0? Would you know what to do to get that answer? You see, I have a position function that's related to time. I have a velocity function that's related to time. And I have an acceleration function that's related to time. So when I asked, where is the object when the velocity is 0, you'd probably have to figure out when is the velocity 0 first. You get some times. And then once you had those times, use them here to figure out where the object is. Does that make reasonable sense to you guys? You follow along with what I'm suggesting. Now, I'm not going to ask you to find the zeros of a function like this, but I am going to suggest that you could find the zeros of a quadratic function. I think that's not unrealistic, so I think we could probably work within that kind of area. So zeros of quadratics, zeros of linear functions are fair game. I could expect more, but it's pretty, I don't want to be spending so much time on the minutia of this mathematics. Does that make sense? So I will ask those kinds of questions. That's in your homework right now, that idea. Now, here's what I want to see. You can go a little further. You learn the polynomial process for the derivative. Do you kind of see there's a pattern to it? If I have velocity equals 6t squared plus 8t, let's say plus 2. It should not be hard to get the acceleration function, right? We just talked about that. We know that this is applying the derivative. But what if I wanted to go backwards to what was there before, the position function? Can you kind of guess at what must have been there before in order for the derivative to have given you this function? Can you try it? So it's just running the process backwards.